Alright, in this video we're going to continue with section 7.2, the disk method, and we're up to example 4, integrating with respect to y. And here we're going to have a two integral case. We're going to need two separate integrals to come up with the volume of this solid of rotation. So find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1. That is an upward opening parabola, y-intercept of 1, and here's our parabola. Y equals 0, so that's the x-axis. The line x is 0, that's the y-axis, and the line x is equal to 1. So we're going to take the region between those lines and we are going to spin it this time around the y-axis. And notice the book is nice and all the pictures, they give us our axis of rotation with that little blue arrow. So we are revolving around the y-axis. In all previous examples, we were rotating around the x-axis, so our representative element, our little rectangle under the curve to determine our upper and lower radii, were perpendicular to the x-axis. Well, now in this case, since we are integrating with respect to y and rotating around the y-axis, our representative rectangles are going to be perpendicular to the y-axis. So the first thing we have to identify are the outer and inner radii. So capital R of x is our outer radius, and lowercase r of x is our inner radius. And you know, these really come together when you look at the picture and the representative elements, those little rectangles. So we're on the y-axis. The upper, or the higher of the radii, the outer radii, is going to be the one that touches the top of the rectangles. And from the y-axis's perspective, you know, here is where we touch the top of these rectangles. And it's the same for both intervals. We're going to have our outer radius is simply 1. Now the inner radius is broken into two separate pieces. As we're moving along the y-axis here, when we integrate between y equals 0 and y equals 1, here's our inner or bottom radius, touching the bottom of this rectangle. And as we integrate from 0 to 1, our lowercase r of x, our inner radii, is just going to be 0. But look what happens when we integrate here between 1 and 2. Now the bottom of this representative rectangle is touching this piece of the parabolic curve. So from 1 to 2, we're going to have a different lower radii. And what is that radii going to be? Well, our given function was y equals x squared plus 1. But we are integrating with respect to y. So we want to solve this and have this equation as x equals something. You know, we want our function to have y's in it since we are integrating with respect to y. So if we subtract 1 from both sides and then we take the square root of each side, we're going to get x equals, well, it would be plus or minus the square root of y minus 1. But here in the picture we see that, you know, we are dealing with everything in the first quadrant. So we wouldn't be interested in the negative root there, just the positive one. So as we integrate, and let me clean up this picture a little bit. As we integrate along the y-axis between 1 and 2, you know, our upper radii is still that 1 that we found up here, capital R of x. But the bottom of the rectangle is going to be touching this part of the parabolic curve. That is our lowercase r as we integrate from 1 to 2. Square root of y minus 1. And that, I think, right there is probably the hardest part of this setup. Coming up with, you know, those representative rectangles, those representative elements, and figuring out your upper and lower radii, or your outer and your inner radii. So now that we have that out of the way, you know, actually setting this up shouldn't be too bad. So the volume is usually the integral from a to b of the outer radius squared minus the inner radius squared, and those radii are capital R of x minus lowercase r of x. And you know, this would be the integral for a single setup. We are going to have a two integral case because we're integrating from 0 to 1 with one inner radii, and then from 1 to 2 with a different inner radii. So we are going to use this twice, and we're going to have to add them together. So let's start working on the integral for our problem. So first, we're going to integrate. Remember, here we're moving along the y-axis. We're going to integrate from 0 to 1. And our upper radius is simply 1. 1 squared minus lower radius is the y-axis itself, so that's going to be 0 also squared. Ooh, and I almost forgot pi. We got to have that pi in front. That's what makes it a volume. So pi integral from 0 to 1 of upper radius minus lower radius. And then we're going to add to that our next integral, pi, and then times the integral from now 1 to 2. Here we are on the y-axis, we're at 1, so we're working our way up toward 2. Our upper radius is still 1, so capital R of x for here is still going to be 1 squared. And then we're going to minus the lower radius, also squared. And here our lower radius is this part of the parabolic curve, which we solved right here as the square root of y minus 1. And this we're integrating with respect to y, so that's going to be dy, dy. And now that I see it, you know that should be a y in there also. Capital R of y and lowercase r of y. Oops. Okay, so let's see what we can do to clean this up a little bit, make it a little more presentable, so we can integrate it nicely. So we start out with our pi, 0 to 1, and this is nice. 1 squared minus 0 squared is just 1 dy. Plus, we have our next integral, pi, times the integral from 1 to 2. And here we're going to have 1 squared is 1, minus, and the square and the square root will cancel. So in the parentheses we'll have y minus 1. And then if we distribute this negative, it'll be a negative y and a plus 1. So 1 plus 1 is 2, 2 minus y. 2 minus y dy. Okay, so we've simplified each integral a little bit. Now we're actually ready to take the antiderivative. So here we're going to have pi. The antiderivative of 1 with respect to y is just y. And we're integrating that from 0 to 1. Plus pi, and our second antiderivative is going to be 2y minus y squared over 2. And that is also integrated from 1 to 2. So the integration wasn't bad. Now we're ready to evaluate and find our final answer. So plug in the upper limit. We're going to have pi. Upper limit goes in, we get a 1, minus lower limit goes in, we get a 0. 1 minus 0 times pi. Plus. Upper limit goes in, 2 times 2 is 4, minus 2 squared is 4, divided by 2 is 2. So there's our upper limit. And now we're going to minus our lower limit evaluated. So we plug the 1 in. 2 times 1 is 2. 1 goes in for this y, and 1 squared over 2 is 1/2, minus a half. So the first chunk here, pi times 1 minus 0 is just pi, plus we're going to have pi times whatever comes out of these brackets. Well, if we distribute this 2, it's going to be a negative 2, and it's going to turn this into a plus a half. Well, 4 minus 2 is 0, so that's gone, and we're left with a half times pi. So pi plus a half pi is 3/2 pi, or 1 1/2 pi, or 1.5 pi. And there's example 4, that is integrating with respect to the y-axis. Remember, the big idea is those representative elements. We have our little rectangles between our radii, capital R of x and lowercase r of x, or r of y. Capital R of y, lowercase r of y. The representative rectangles exist between those curves or lines. Example 5 is a good manufacturing example. A manufacturer drills a hole through the center of a metal sphere of radius 5. So our radius, or this metal sphere, has a radius of 5. The hole that we drill through it has a radius of 3. What's the volume of the resulting metal ring? So here's a nice little 3D picture of it. Now imagine we want to take a knife and we're going to slice that open right along the X and Y axis. So, just a quick sketch here. Here's our X and Y axis. If we're looking at this as two-dimensional, here's our circle, and it goes from 5 to -5, 5 to -5 on the Y axis also. And we want to find the result, the volume of that metal ring. So we need a formula to work with. The area, or not the area of a circle, but the formula for a circle in the plane is x squared plus y squared equals r squared, or radius squared. Here our radius is 5, so we square it and get 25. We are going to be spinning this around. Here's the hole we're going to cut through it. So we're going to be spinning our slice around the x-axis. So we're going to be integrating with respect to x. So we want to solve this equation for y. So the first thing I would do is subtract x squared from both sides. And then I would square root. Y is going to equal the square root of 25 minus x squared. And we're going to need to know on the x-axis, where will we begin and where will we end our integration. If a picture is available, you can get the information off the picture. Let's assume in this case we did not have the picture. Where would we begin and end these points of intersection? Well, we know that the hole has a radius of 3. So we would plug that 3 in for our y value. How high up is this? A radius here of 3 means that this line y equals 3. It's going to be one of our radii, and we could plug that y as 3 in right here. X squared plus 3 squared, or 9, equals 25. Subtract 9, x squared is 16, and when we square root, we get plus or minus 4. So our integration is going to begin at -4 and end at +4. Now let's think about our representative rectangles that exists between our upper and lower radii. So here's just a cross section of it. Here's the hole we drilled through the metal sphere. So we have our upper radius, looks like it's going to be this curve. Root of 25 minus x squared. So r of x, capital R of x, is our radical. 25 minus x squared. And this setup is nice because this is the upper function, or the upper radius, the entire way across. We're integrating from -4 to +4 the entire time. That is our outer radii, our capital R of x. And we can see under it here our representative rectangle, our representative element. The top of that rectangle is touching that curve the whole way across, no matter where I draw that representative element. What is the bottom radius? What touches the bottom of all of these rectangles? That is lowercase r of x, and that's just a nice, easy 3. So let's see, I think we're ready to start our integration. The formula is pi, definite integral from a to b, of capital R of x squared minus lowercase r of x squared dx. And let's plug in the numbers relevant to this problem. So pi, and then we are integrating from -4 to 4. First is outer radius squared. And our outer radius is that piece of the curve. Root of 25 minus x squared. And then we subtract our inner radius squared. And the inner radius is just that simple horizontal line, y equals 3. So, just sort of like in the last example, or maybe it was the one before that, we have a squared square root. Those will cancel, leaving what's under there, 25 minus x squared. And then we're going to have minus 3 squared is 9 dx. And let's see, we do got a couple like terms we can combine in there. We just have some numbers, the 25 and the minus 9. We're integrating from negative 4 to 4. 25 minus 9 is 16 minus x squared dx. Nice easy two-term polynomial. We're ready to take our antiderivative. 16 integrated with respect to x is 16x minus x to the third over 3. And we will evaluate from negative 4 to 4. So let's see here. Time to evaluate. Pi stays out front. Plug in the upper limit. 16 times 4 is 64, minus 4 to the third is also 64, and that's the numerator over 3. So there is our upper limit evaluated. Now we're going to subtract our lower limit evaluated. So we plug in the negative 4. Negative 4 times 16 is negative 64. And we'll have a negative 4 to the third is negative 64. It's going to hit this negative and become a plus 64 thirds. And let's work within those parentheses and brackets. Let's see here. If we distribute this negative, this is going to become a plus. And if we distribute the negative here, this is going to become a minus. So we have a 64 plus 64 is 128. And we have a negative 64 thirds and another negative 64 thirds, which is negative 128 thirds. And then that quantity is times pi. If we work within those brackets, we will get a 256 pi over 3. Now there's another way to do this. If you recognize that this function is symmetric about the y-axis, if we focus in on this picture here and we slice that right down the y-axis, it is symmetric. So the area from negative 4 to 0 is the same as the area from 0 to 4. So if we wanted to go back to our integral, we could say, well, instead of integrating all the way across from negative 4 to positive 4, we could just integrate from 0 to 4 and then double that answer. So we could just double this if we make our lower limit into 0. And you're going to see that this works out to be the exact same answer with less work. So the 2 pi is out front. Drop in the upper limit, 64 minus 64 thirds. And then we would drop in our lower limit, 0, and get a minus 0. And then we would just distribute this 2, and we'd have pi times 128 minus 128 thirds. And that looks just like what we found before. Final answer will be the same, 256 pi over 3.